Thank you all for being here. So tonight we're going to talk about quantum computing. And I'm sure that we have a lot. This is a pretty cool crowd tonight. We have all kinds of different people here from all kinds of backgrounds, and I know that some of them are totally up to date on what we're going to talk about, but some are not. So to be fair to those who are not, let's kind of go quickly through, the primer on this, sure. And then we'll do a little deep dive on challenges, the future, and that kind of thing. So at the beginning, what is a quantum computer? DWave, by the way, I'll just preface this by saying, DWave, I've just spent some time with Vern up in Burnaby and BC, and from our perspective, there are many definitions of what is quantum computing, and we'll go through some of that, but we think that DWave is the most commercially advanced company in the world selling real product today to real customers in one part of the world, the academic definition of what is quantum computing. So we'll now do some definitional things and some framing things. Vern is excellent at this, and I think in a very short period of time, you may not understand quantum mechanics, but at least we'll kind of help you understand where DWave lives in this world of. So would tell people, what is quantum computing?
Sure. Absolutely. Well, thanks, Mark, and thanks for inviting us here. It's really a pleasure to meet all of you, and hope to get a chance to chat with all of you today. Just by way of background, I'm not a scientist, so I'm giving you a layperson's description of quantum computing. I've been with DWave about 6 years. My background is in the old-fashioned classical computing and kind of the enterprise computing world. But this has been the most fascinating thing I've ever done in my career, and it really is an amazing company, and I'm thankful to have the opportunity to lead a company like this. So a quantum computer is most simply a computer that leverages directly the laws of quantum mechanics. Now, as you all know, quantum mechanics were discovered about 100 years ago by these great scientists, Schrodinger and Niels Bohr and Einstein and others in the early 20th century. And it completely revolutionized our view of physics and how the world operates. And there's still, still unknown areas about quantum mechanics and how it actually works. And there's lots of research and fundamental questions that are being answered about quantum mechanics. But no computer has ever been built that directly leverages these materials, these laws of quantum mechanics directly. Quantum mechanics describes all of nature, so there are quantum mechanical things going on in all devices and all properties. But the difference when you build a quantum computer is you're actually having the quantum mechanics do the calculation itself. And there are different ways, as you would imagine, to build quantum computers. Our founders chose a model called adiabatic quantum computing. It's a mouthful. But this turned out to be a very effective way of being first to the market in quantum computing.
But before you go any further, for those who are on the liberal arts side of this equation, there are three things essentially in the quantum mechanical world that you're using in your compute systems. Yeah. And maybe we could do a paragraph or a sentence each on what those three things are. Yeah. We'll do a duet here.
Okay. Yeah. No, that's very good. So the first interesting property of quantum mechanics that is necessary to build a quantum computer is something called superposition. And this is a particle or an atom or a device that is actually in two states at the same time. And our minds have trouble with that. Like, how can something be both black and white at the same time?
Imagine two waves, like two light waves that are crossing each other, and as they cross, they don't interfere with each other, but they pile up. So instead of getting two halves, you get one whole. That's superposition in a probabilistic sense. Fair enough?
Yeah. So superposition is an interesting property, and what a quantum computer does is they all develop a thing called a qubit or a quantum bit. So most of you know, like, computers today are built on 0 and 1. That's kind of the most fundamental object or digit, I guess, in computing. A qubit or a quantum bit can be 0 or 1 like a classical bit, but it can also be 0 and 1 at the same time. And that's interesting, but it doesn't really get interesting until you start stringing these qubits together. So for instance, our computer has 1,000 qubits in it. And so you can represent numbers of 2 to the 1,000 different types of numbers. 2 to the 1,000. So 2 to the 1,000 is, I think, 10 to the 300th power. There's only 10 to the 80th atoms in the universe. So this is an absolutely enormous number of...
More than there are atoms in the universe.
Yeah, there's only 10 to the 80th, scientists estimate 10 to the 80th, maybe 90th atoms in the universe. This computer can search through answers of up to 10 to the 300 different possible answers at the same time. And that's the core of where it gets its parallelism or its power. It's not precisely parallelism, but it's exploring an answer space of all those different possibilities at the same time. And it's leveraging nature to do that property. So at its sort of lowest level, this quantum computer that we built is basically just taking this piece of matter and giving it a problem and having nature solve this problem and then getting a result from it. Now, it's a very complex thing. I'm getting away from the sort of 3 properties of quantum mechanics, but it sounds easy, but it's very hard to do because in order to have a quantum mechanical operation go on, you have to be in this very rarefied environment. So this machine operates down at what's called 10 millikelvin, which is 0.01 Kelvin degrees away from absolute zero.
So before we go into the beauty of the machine,
yeah. Oh yeah. So I'm going to go back to to your point, the 3 properties of quantum mechanics that are necessary to build a quantum computer. Entanglement is one. So entanglement is a really interesting property where you can have one of these qubits or a quantum mechanical atom or whatever it is, and you can then have another, and if if I change the state of this, that bit over there will instantaneously correspond to that state. Right, and that's at a distance. That's happening within our processor. Our processor is only the size of your fingernail, so it's not at a distance.
These are linked together in some eerie way that Einstein called spooky.
Spooky at a distance, yeah. And scientists still don't understand exactly how this happens, but there have been experiments where they've actually taken these quantum mechanical objects and separated them by hundreds of kilometers and changed their state, and it changes magically 100 kilometers away.
Magically linked. Things are linked in a way that we don't yet understand how.
Yeah.
But they act instantaneously as a set.
Right, right. So that entanglement is an important part of what physicists look for in a quantum computing system. And then the third property is called tunneling. And this is, many of you may be familiar with like energy barriers. You can imagine like if you have a 3-dimensional landscape and you're trying to find the lowest valley in this 3-dimensional landscape. In order to do that, you sort of have to traverse all these different, the entire map to find, what is really the lowest value. And computer scientists have developed what's called heuristics to sort of get to that lowest valley very quickly. But what winds up happening is they get stuck in a valley that's not the ultimate lowest valley, right? You get stuck in what are called local minima. And tunneling, or quantum tunneling in this example, can help you go through those barriers and magically, I hate to use that word magically, but get to that lowest valley in that landscape. Now you might say that's an obscure problem.
So here's the metaphor that I would use. You're at home, you've put the fireplace together, you get all the wood and the paper, but you haven't lit the match. Normally, you have to create the activation energy, which is like going up over the you have to create an event which lights the fire. But with tunneling, not required. The fire lights itself. That's right. And so then we're going to move into optimization in a minute. But go ahead with
So yeah, that is exactly right. That's another way to describe tunneling. So we use tunneling to do this optimization problem. So what I mentioned there is a metaphor for the real problem that this computer solves, which is an optimization problem. And it sounds like an obscure problem. Why do I need to find this lowest valley in this 3-dimensional landscape? But that describes many problems which are all over the place in finance and in machine learning and in logistics, and many of these problems scale very poorly on classical computers. So when I say classical computers, I mean computers that are built the way they have been for the past 70 years today, that are doing amazing things, but there are certain problems that are could be beyond the scope of classical computing. And those are the ones that we're most excited about, problems that may forever be beyond the reach of classical computers that a quantum computer can solve. And those can be in finding cures for cancer, or even as pedestrian as helping Wall Street monitor their risk better with value at risk calculations and things like Monte Carlo simulations that they do. And the host of applications is very wide and very human scale, very, very important and impactful types of applications. So we're happy to be the first to provide this kind of capability. And I would characterize the capability that we have as it's still early days. We've done our 3rd generation of our system here. And we have found applications of the technology that outperform classical computing even today. But to think about it, the bar is quite high. Classical computing has increased dramatically over 70 years or so since those first computers came out in the 40s. But yet in our 1st generation, and then think of all the software improvements that have been made, including the hardware improvements. In our 1st generation, we were able to outperform that entire ecosystem of hardware and software development for very small benchmark problems today. But with each subsequent generation, this computer is becoming more and more powerful, and the application scope grows dramatically.
So let's talk about problems for a minute, because that's a key way, I think, of understanding the power of what you're up to here. The von Neumann, so far, the traditional classical architecture of computer says take 2 + 2 to give me 4. It's a linear thing. It can be done very, very, very fast, but it's still a linear 2 + 2 is 4. You want to do it again? Do it again. There's no speed advantage at all. But what you're talking about with this computer is it's not parallel computing, but it's like parallel computing, where you look at a very large number of parameters and values at the same time. You come up with one or thousands of solution sets which optimize the best way to do something, right? And you might describe 2 or 3 big problems. You mentioned cancer, but everyone's curing cancer. So give us some other problems that are really well suited to what you're up to.
So let me just say that, as you alluded to, that this machine does really at the base level, it solves one problem, which is an optimization problem. So it's just very, very good at that optimization problem. And so as I said, it can search through these possible range of answers of this absolutely enormous number, and gets its parallelism really from nature. It's leveraging these quantum mechanical properties to get that parallelism. So then the question becomes, how do you take advantage of that? How can you craft that optimization problem into real problems that are meaningful to us? And it requires a new set of algorithms. So we have software developers that work with our customers to craft that base level optimization problem, which is very, very powerful, to something that's meaningful. And it's different than von Neumann computing, and different than the way we've thought about computing, the way I grew up in computing. It really requires a different set of tools and so on that we're in the middle of developing. But having said that, we've done some interesting early things that I think are quite exciting. And they range from, I'll give an example in machine learning, where we worked with Google, who's now a customer of ours, to, their problem was they wanted to optimize Google Glass. And Google Glass, as you remember, one of the inputs for Google Glass was a thing called a blink. So you could blink at it, and it would actually use that as a menu input. But the problem they had is, how do you tell the difference between a wink and a blink? An involuntary wink. And so if you're a programmer, you can't really sit down and develop that algorithm. The way you do that is you use machine learning techniques, or these AI techniques that are becoming all the rage, and really is doing things at Google, from their self-driving cars to PageRank and everything else. So they developed, or we co-developed with them, an algorithm to look at videos of people winking and blinking, and then determine what the difference is between a wink and a blink. and learn that process. And then you take that piece of code and put it inside Google Glass. So that becomes, you know, it's called the determinant of what that blink is, right? And you can take that code piece and put it in there, and it's very efficient. And we found out that, you know, this code was more energy efficient because it used less power, and it was more accurate. So that's an example of where you could use a computer like this to do a machine learning exercise.
Google has some other things they're doing with your machine.
Yeah, so they have created what they call the Quantum Artificial Intelligence Laboratory, and it's actually hosted at NASA Ames in Mountain View, California. And they're collaborating with NASA to develop all kinds of applications for our quantum computer. NASA's doing things like exoplanet research, or looking at, you know, this vast amount of data they have from their various spacecraft that they're analyzing, looking for planets outside of our solar system. So that's like one example of an application.
And they'd like to drive their rover, like the Mars rover, probably with an optimization program that you guys might be able to.
Well, ultimately, you know, I think that is one of the applications, but they're exploring quantum computing as an important tool for lots of mission problems that NASA has. So that's the stated purpose of the laboratory. And then Google themselves, you know, they really are developing machine learning algorithms. How do we use this capability to do machine learning? And we're doing a lot of work in that space as well, and finding new algorithms again, and to do these machine learning tasks, which are, machine learning is probably the most interesting thing going on in computer science today. It's a very powerful mechanism, and I think is going to be the basis for most of the technology innovation that we see over the next few decades. And we're just seeing the tip of the iceberg of what artificial intelligence can do with machine learning. So it's our belief, and I think Google's belief, and NASA as well, that a quantum computer is an important tool for in the machine learning space. Yeah. Another, you know, maybe a little bit more pedestrian example is when I worked for Goldman Sachs. I ran technology for them for about a decade, and the biggest workload that Goldman has is doing something called Monte Carlo simulation, which they're basically trying to look at their balance sheet and the individual positions and trading positions in the firm, and understand the risk that's associated with that. So they run all these different scenarios of interest rate.
Thousands of scenarios, thousands of risks.
Yeah, and it's an exhaustive process, and they literally have millions of computers that do, not millions of cores, if you're familiar with cores, but millions of cores that do nothing but run this calculation 7 by 24. And that is a brute force way of doing it. That is a problem that is much better suited for quantum computing. So, you know, I believe eventually that entire kind of workload you'll see move to a quantum computing type of environment. And there's a thirst to do that. Right now it's almost a batch process where, you know, once a day, Lloyd or someone at Goldman gets this roll-up of the risk of the firm. They'd like to do it real time, but it's just not possible today. So that's an example of where the computational capabilities are just too enormous, and you'd like to do more scenarios, more interrelationships of securities and things like that are just not possible today. So those are examples of how you would use this capability.
I was just talking to Steve Lohr about the world and the compute world together and how they're related to each other going forward. It seems to me as though we're leaving kind of the 1950s era, which is the von Neumann era, of this kind of single linear, and whether it's in medicine or the stuff you're talking about, I think part of what's happening is we're just finally accepting that the world is a very, very complicated place. And we didn't have tools to understand that complication, so we just didn't talk about it. Right. Take this white pill and go home, and if you don't make it, that's too bad, you had to die. But it turns out that we just didn't understand how cells work or anything else. And so now we're going to actually take that dive and look at the complexity of the universe. And I suspect that whether it's the machine you've got to sell tonight or something 20 years from now, but that quantum computing will play a pivotal role because of what you're describing. That it has the ability in one instant to look at a very complicated situation and optimize for many, many thousands of different parameters. Instead of having thousands of people sitting at Goldman Sachs, each one saying, I'm going to do this bond market, I'm going to do that bond market, You have one thing saying, just give me the portfolio. Is that a fair description?
Yeah, it is. And so I agree with you, and I agree with the characterization. This is really the dawn of the quantum computing age. I sometimes characterize it as, if you think back to even in 1974, Intel came out with their first microprocessors, which weren't particularly powerful at the time, and there weren't many tools for them, and the applications weren't well understood yet. But these guys, Paul Allen and Bill Gates, came along and wrote this first software for that microprocessor, and that was really the dawn of what we called back in those days the personal computing age, which ultimately became the computing age. And most of what we do today is kind of based on that groundwork that was done back in there. It feels similar today at this dawn of quantum computing, and some of the applications for this we don't even understand today, but it will be a fairly dramatic capability. We're not going to be the only ones. We want, it's our goal to dominate this space. We think by being first and understanding how to build the infrastructure and build the chips and build the software for this, we can have a long range, long-term advantage over any competitor in this space. And not that we are going to rest on our laurels at all, but we think we have a unique advantage because of the choice of model that we've made, and because we've had this very focused venture-funded effort for now 15 years that we've been doing this, that we're in an incredibly unique position. And one other point I wanted to mention, it's not a replacement for computing. We won't replace all of classical computing. This is a resource that will be used alongside classical computing. And ultimately, I think it's going to, this capability will be in the cloud like all computational capabilities. I'm firmly convinced that all computing is moving to the cloud, and we've seen dramatic progress on that in the last few years. And you can envision a software developer just a few years from now will make a decision on how they're going to implement a particular algorithm or a particular program, and they'll just use, even an iOS device. They'll access the quantum cloud versus the classical cloud, and it will be as ubiquitous a resource as classical computing is today, focused on a different set of problems.
So just because I know there are some people who are a little more sophisticated and they would want to know the answer to this, and it's a moving target. There was a lot of controversy and discussion, and you and I have talked about this earlier in the company's history about what is quantum computing. Are you really doing it? Yes. And if you would, for 2 minutes, talk about the answer to that question, that would be helpful to people, I think.
Sure. So as I mentioned earlier, the founders made an important choice back 15 years, or 10 years ago now, I guess. So the company was founded in '99, and the first 5 years was really gathering IP and understanding how to build quantum computers and making a decision on what the best way to build a quantum computer is. And at that time, they made a prediction that this model of adiabatic quantum computing was the best way to move forward to get to a practical quantum computer as soon as possible. Or otherwise known as quantum annealing, yes. And that turned out to be the right decision, because back those days they were saying it was going to be 10 years before this other type of quantum computing that most of the rest of the world was doing. It's called the gate model or circuit model of quantum computing. They said that was 10 years away. And now, I was just at a conference, the conference that you and I were at, that they're saying it's now 10 or 15 years away. So there's really little or no progress made on that model of computing, because it's just really hard. There's nothing fundamentally wrong with the approach. It's just really hard to do. We just, it's the insight of the founders. They made the right decision. They had a very focused effort to build this. And we're kind of an interesting company, because we're half in the science world and half in the sort of venture-funded technology world. So we actually publish lots of peer-reviewed papers. We've done 60 peer-reviewed papers, and in the last few years we focused a few of our publications directly on those questions. Is this really a quantum computer? So we effectively have put those questions to bed, because we've demonstrated the quantum mechanical properties that you talked about earlier, superposition, entanglement and tunneling. We've shown those in scientific peer-reviewed papers. So a lot of those questions have gone away. And in fact, now the US government, who was one of the big skeptics when I first joined the company, they have their own quantum computing effort, and it's adiabatic quantum computing. It's the model that we are doing. So there's there's lots of validation now, and the world is sort of understanding the difference and is getting on board with the choice that we made. So when I first came on board, there was lots of controversy. In fact, I was telling the story earlier when I was talking to the recruiter about this opportunity. I'm sitting there Googling DWave, and I'm finding all this negativity, and it's not real quantum computer, and blah blah blah. And it really is that a distinction of the model of quantum computing, and where everybody else was thinking there's only one way to do quantum computers. Interesting enough, Microsoft, for instance, is doing their own model of quantum computing. It's called topological quantum computing, which is very elegant, but it's going to require the discovery of a physical particle called a non-abelian anneon, which no physicist has actually seen yet. So once they find these things and figure out how to generate them and manipulate them and all that, then you can start building hardware. I mean, that's like a multi-decade effort. But give a credit to Microsoft for such far-reaching research and a very elegant part of quantum computing.
So having had the advantage of being up with you in BC, I've seen the boxes. And I would like you to describe a box. We'll do that, we'll do the future after that. But the boxes are very cool. But of course, like all boxes, they look cool, like Cray. I mean, they look beautiful. They have these really cool neon lights and stuff. But when you go inside the box, tell people what's inside the box.
Yeah. So the box is like the size of this stage, but 10 feet high. It's 10 by 10 by 10. Inside is really just this one little chip. It's the size of the microprocessors in your phone. It's a superconducting chip, so it's built using semiconductor manufacturing like any other chip, but it's a very unique type of chip. And most of the bulk of the machine is taken up by actually the refrigeration mechanism to get down to this incredibly low temperature that I was talking about earlier, 10 millikelvin, which is minus 273.15 degrees C.
It's colder than space.
It's hundreds of times colder than space. So there's no natural environment in the universe that's as cold as this. And this is
the coldest place.
It's the coldest place in the universe unless there's other intelligent life in the universe that has better, colder places. But so and not only that, it has to be in effectively a magnetic vacuum. So we have all this. We have like a Russian scientist that specializes in magnetics, and he's built the best magnetic vacuum in the universe. And so that chip is in this extremely cold, extremely low magnetic field. Of course, no air, no interference at all. And all of that bulk is really the shielding and the refrigeration technology to just put this chip, this little tiny chip the size of your fingernail, in this pristine environment. A lot of you may remember from physics class, temperature is molecules moving around, right? So if we can get down to that absolute zero, and you can't actually get to absolute zero, it's not possible, because then, I don't know what would happen actually if you did that. But it's an asymptote. You cannot get to absolute zero. But the closer you get to it, the less those molecules move around and the less thermal interference you have. So these extremely exotic conditions are necessary to have this computation be successful. So we've had to build this crazy, exotic box.
A lot of money on refrigeration.
Yeah, and this is state of the art. I mean, these are very, very cranky refrigerators too to do. We call them fridges, but they're incredibly exotic in their nature. So then we have to get all the signals down into this little chip and back out of this chip. So that's what that big box is like. And ultimately, we'll be able to shrink that down a little bit. But size isn't that important in this space, because ultimately these will be in someone's data center, in a cloud provider data center that we'll partner with to put hundreds or thousands of these machines in there, and then they can be accessed, kind of by the service, through the internet. So. But it's unlikely, at least in my lifetime, that you'll see them in laptops or things like that, because of the very exotic and pristine environmental conditions that these refrigerators these chips need to be in. One interesting side effect, though, of this, the fact that it runs at this very low temperature, is the processor itself generates no heat. So like if you're familiar with data centers today, like Google's and others and data centers, they have to put them near hydro plants or hydroelectric plants because they use so much energy, and it's the #2 consumer of energy in the world is data centers now. These chips have the advantage of they dissipate zero energy. So it's only the refrigeration technology that's an electrical and heat load, and that's modest. It's like 20 kilowatts, which is almost trivial for data centers today. So it could be a huge energy savings as we move applications to this type of computing platform.
So take us forward, and then we'll do a couple questions. We don't have a lot of time. Go forward maybe 10 years, not 100 years, but 10 years, 5 to 10 years. And you're at 1,000 qubits now, is that right? So what do you see 5 or 10 years from now in terms of either, the chip itself or chips, or if you, in terms of problems that could be solved?
So we're on sort of a clockwork pace, much like back, if you go back to Intel, they come out with a processor roughly every 12 to 18 months. We've done that now for 3 generations in a row, 3 production generations in a row. So we're going to continue on that product cadence and sort of doubling the amount of qubits, the capability, which roughly corresponds to the capability of the processor, and improving the performance on multiple dimensions. So in 10 years, we'll have, say 5 to, 3 to 5 generations of the processor, and be literally at tens of thousands of qubits, and we'll clearly be in this Goldilocks zone where we'll be solving problems that if you took all the computers in the world and put them together, you couldn't solve these problems classically. And those, I think, are
literally solving problems that could not be solved.
That could not be solved any other way, and even.
Is there a name for crossing over that line?
No, there isn't, but there should be. There should be, yeah. And that's kind of the holy grail of quantum computing. You get to that level where you're solving these human scale problems, climate modeling, right? We've had an early indication of this. We work with this small startup company in San Diego that's developing oncology cocktails for stage 4 cancer patients. They basically do this they do a genome sequence. They run it through this process where they try to find basically these kinase inhibitors, and they have a crystallographic library for all known existing oncology drugs that treat these forms of cancer. And they do this exhaustive calculation where they're basically trying to, at a very detailed molecular level, match these drugs to to do this. And they've done this process for 4 stage 4 cancer patients, and 3 of them are in remission. And all they've really done is pick the optimal cocktail of off-the-shelf,
optimizing,
the mixture of drugs, to maximize the effectiveness for those patients. So that to me is like an early indication of what can be done in the area of personalized medicine and computational, bioinformatics, and these really important, impactful problems that we hope to be part of in the future. Yeah.
Okay, so I think what we should do now is open this up to questions. We have a few minutes, and if you have any questions for Vern, Sharon.
That was breast cancer. The company is called DNAseq, and they're located in San Diego. They're actually looking for funding if anyone's interested in that. But a great little company. The CTO there was the gentleman that designed Gleevec, which is, I think, one of the most effective cancer drugs to date. Yeah.
Questions? Very quiet. There's one.
So, if you look at Moore's law, it's predicated on shrinking the distance between gates by a factor of 2 every 12 to 18 months.
Yeah.
The number of qubits grows, as you said. What's the underlier that drives the growth in the number of qubits that you can support?
Yeah, that's a great question. So, and one of the things that the industry talks about and people are concerned about is they're sort of the end of Moore's law, which we're starting to get to. We're tailing off on the ability to develop these chips at these 10 nanometer level, where you start to get down to atom width, types of chips. One of the nice things about the technology that we're using is it's 25 or 25 microns. So it's 250 nanometers. This is like a line width that companies like Intel were using back in the 90s. So we are nowhere near approaching the limits of Moore's law. We have, you know, decades of development before we'll even have to start thinking about that. So that's a real advantage, and companies like Intel, you know, have been talking with us and are interested in this because they're facing kind of a, you know, existential crisis, and, you know, what happens at the end of Moore's law? What can they do? And, you know, quantum computing and other, you know, novel computing techniques are really going to be necessary in the future, because otherwise we're going to run into this situation which we've never been in before in humankind, where the power of computers flatten out because of Moore's law. So it's a great question. Thanks.
Doesn't cooling a chip generate a heck of a lot of heat?
No, so yeah, the cooling actually is only 20 kilowatts. So that whole refrigerator, that whole box that I talked about is 20 kilowatts, which in my experience is, if you go into a data center, that's about like a quarter of a cabinet of these racks of servers that you typically see in a data center. So it's almost a trivial amount of power. And the cool thing is, the important thing is, as the capability of the processor scales, that we put more and more qubits on it, there's no heat load, so it'll always stay at 20 kilowatts. So you can imagine these computers getting enormously powerful in the next, you know, 5–10 years, but the power footprint is exactly the same. Contrary to every, you know, I'm an old data center guy, and you spend all this time engineering data centers and trying to cool them better and be more efficient and so on. This completely changes that equation. It's pretty exciting. Another question.
Can you compare or contrast the load and store notion of conventional computing with quantum?
Yeah, there is really no comparison. It's a complete, it's not a, as you were saying, a von Neumann. So load and store, or is another way of saying a von Neumann computer, which goes back to John von Neumann in 1948 and invented the first electronic computers, actually at Los Alamos Labs, which just became a customer of ours just last month. They have a very rich heritage in computing, and, you know, we just are going to be installing a system at Los Alamos Labs where the first computers were ever built. So those load and store computers are sequential instructions, as you were talking about earlier, and you just run through many of these instructions very quickly. This machine does one, it actually has one instruction. It's this optimization problem that we talk about, and you have to craft your problem in terms of that optimization problem, which we have lots of techniques and tools and so on to do that, but it's a challenge. It's a different mindset for programming. But if you craft your problem into that, you can then explore that huge number of different alternatives and get to the optimal answer in one instruction. We call it a quantum machine instruction, if you will. So it's very different. So we do one thing, and we do it very quickly with a lot of parallelism. But that problem can be morphed into almost anything. You can solve almost any problem using that capability, but it's a challenge to do that sometimes. Question in the back. It's Steve.
Can you talk a little bit about the development of software? Is it open source that you're doing, or in the migration of quantum computing into the cloud? How important is software, and how do you see that? Where are we, and where are we going?
Yeah, so we're at the very early stages of developing our software ecosystem, and we've got kind of a multi-pronged approach, as you can imagine. So one thing we want to do is enable partners to succeed in this space. So DNA-seq that I talked about earlier, doing these oncology drugs, oncology cocktails, if you will, is an example of a partner that we work with and co-develop algorithms. We have another company called 1Qubit that's developing financial software, portfolio modeling software for our platform. So we want to enable these partners to develop and give us leverage, really, with the capability. So we have a toolkit. It's very early because, you know, we've had to develop the hardware and the chips and all this. The largest part of our investment moving forward is scaling out that software ecosystem. So we want to get it to the point where it's just as easy to use. There's like a Python interface. You can use a Python-like language and program, you know, these very complex problems without having to understand physics at all, the icing model or the cubos or these optimization problems that I'm talking about. You can state your problem in the way that normal programmers like I used to be and you used to be back in the day, and take advantage of that. But we're not there yet, and that's part of what we need to do in the next few years. To ultimately, it will be available in the cloud to anyone, and we can have all the great minds in the world trying to implement algorithms. Some algorithms we're going to want to take in-house because they have a lot of value in themselves, but most of the tools and technologies we will be open sourcing because we want to foster this software ecosystem. And it's one of the most important things that we need to do scaling the business.
Okay, well, I think we're out of time, sorry. And, okay, Doug. Make it quick, though, make it quick.
So just maybe as we're heading to predictions, one prediction, right? So you talked about quantum annealing, what you do, gate source and topological. So lay out a framework, how the quantum annealing's here today, what's the timeline for gate source, what's the timeline for topological, and then how will they interact with each other?
Yeah, so I think my view is they'll all be complementary. So they'll all continue to, ad infinitum as they're developed, right? So there will be important applications for quantum annealing as well as gate model moving forward. So time frame wise, I think you won't see gate model computers for about 15 years. Usable. I mean, there are gate model computers. The world's largest problem that's been ever solved was factoring 21 into 7 and 3 one time in a laboratory. It's really a proof of concept. Yeah, we all could have done that, I'm sure. So that, it's about 15 years, I would guess. Microsoft's effort I'm less familiar with, but just what I talked about in terms of the hardware, it's probably 30 years away, something like that.
Okay, thank you. So this is pretty cool.